Before we proceed to explanation of my neuron module, let's understand the dimensions because this is where the major confusions happen. So we'll look at the dimensions of my input and output, and then we'll look at the neuron module. So I know that my input for this neuron module is my pixels, right? Pixels or image. Okay. So what is the width of this pixel or image? I'm keeping this as 2W, where W is equal to 8. So the pixel value is 16-bit. The pixel values are 16-bit. That is my input. What are my weights? Weights I have kept it to be with W, 8-bit, 8-bit weights. Bias also I have kept it as W, 8-bit bias. Sorry, 8 bits. 8 bits bias. Okay. Now I know the equation for the neuron module, which we have seen in the when we were looking at the gist of neural network. It was summation of Wi xi plus b. So Wi is 8-bit, xi is 16-bit. This is 8-bit. So this is basically you're multiplying your sorry. So what are we doing here? We are Wi is 8-bit, or you can say this is W into 2W plus W. So when you multiply, basically you're adding the number of bits. So this becomes 3W plus W. So this entire thing, the total, when you add all these stuff, for example, let's say 3W plus W is basically 3W plus W bits. Your 3W bits can accommodate this summation. But when you add this is for case 1. This is W1 into X1 plus B1. But the entire summation is the sum of W1 X1 plus B1 plus W2 X2 plus B2. Like this, the summation goes on. So when you add 3W plus 3W plus 3W, the max to max you can get is you have to, in order to avoid overflow, just for safety, I'm keeping the width as 4W. So the output is kept to be 4W. The width of the output is kept to be 4W to avoid any overflow during the summation. So this was the explanation of the dimensions. We'll now look at the neuron module. We will now take a look at the neuron module. So the neuron module has these inputs, and we have discussed about the dimensions of the input in our previous discussion. So in data, we know it is of 2W width and weight is of width size and bias is of width size. And your neuron out is 4W. And we have discussed why this is 4W. So in the first discussion where we were discussing about the hierarchy, there we have discussed that your in data for your first neuron layer. For your first dense layer, your number of in data will be your 196. For your dense layer, input data will be 196, and your weights, the number of weights will also be 196, and your bias will be equal to your one bias for one neuron. So if you look at one neuron in your dense layer 1, that neuron is connected to 196 weights. This means number of weights will be 196. And how many inputs are those connected to? It is also connected to 196 inputs, because your first layer is your input layer, and we know that my input layer has 196 pixels after pooling. But we have also discussed that your neuron will only have, the output of this neuron will only have one bias. We will not add bias repeatedly. So you have one bias here, and then you have a 4W neuron out. This is the weighted sum of your neuron. Okay, so this is the child module, your neuron module, which is computing the weighted sum for one neuron. Okay, not for the entire layer. For the entire layer, we have seen in the hierarchy video that the dense layer module will instantiate it for 32 times or 10 times depending on your layer, the layer which you are working on. So this is the intermediate wire which is used to store the product, and your out is initialized to 0. Okay, now this product W is assigned to your in data into weight. So why I have used assign statement here? Because the moment your in data changes or the moment your weight changes, your product will also be equally, automatically it will continuously be driven, so it will automatically change. So your product W will reflect these changes as soon as your right hand side changes. Now in the always block, if reset is asserted, all these done, address, out, everything is given the value 0. If enable is asserted, this means it is asking me to start my computation, start my weighted sum computation. At that moment, I will check if my address is less than in size. What is my address? What do we mean by the address here? Since in the previous, for my first neuron in my dense layer 1, if you see, I have 196 inputs coming to it. That means I need to have something which will help me traverse through those 196 input neurons. So my address is specifying that my address will initially be 0, then it will go on till 196 to cover all the 196 input pixels. So I will check if my address is less than input size. So if my address is less than input size, my input size I know it is 196 for my, I'm talking about the first layer now. If you talk about the second layer, this in size will change. This in size will change from 196 to 32, because for your second layer, your input, there are 32 neurons as input. Okay, so your all parameters will change. You will look that in your dense layer 2 module when we discuss about dense layer 2 module, you will see that difference. But for now, just let's just talk about your dense layer 1. So if address is less than in size, this means your total weights are not exhausted and your total inputs are not exhausted. So you will continue adding your out plus product. So this is an example of continuous addition or incremental addition, where so initially what happens, just imagine that I'm talking about the first neuron in your dense layer 1. Initially, what is the value of out? 0. So for the first computation, my product will be the, I will add the weight and the input of my first input to my first neuron in the output, dense layer output. So what will I do here? My out will be 0. So this will become 0 plus W0 X0. So this is basically, for the first iteration, it will be 0 plus W0 X0. After, in the second iteration, again I will check if my address is less than in size. Yes, it is less than in size since I've only reached my second weight. So then it will add in with this W0 X0, since see, whatever previous value of out you had, upon that you add the product. So this is continuously incrementally adding the weights and inputs. So it is giving you a weighted sum as your final output. So then you add W1 X1. Now in the third iteration, you will check my address is less than in size. Yes, my address is less than in size. Then again, you will add this product W. What is my product W? In data into weight. This is what I've done here. In data into weight. In data into weight. Here also now I will compute in data into weight, and that is added to my out. So whatever previous value, what was my previous value for this iteration? My previous value was this. Upon this, I have added my new product. So this goes on till your index is 195 into x 195. Okay, so in total you can see that from 0 to 195, that means total 196 inputs are exhausted, 196 weights are exhausted, and then you have computed the final weighted sum. Okay, this is what this line is doing. And then so this from W0 X0, it moves to W1 X1. How is this happening? This is happening using this line. Address is address plus 1. Since address is incremented, you will, as soon as your address changes, this means your in data will also change, your weight will also change. If these two are changing, this means with continuous assessment, this will also change. Product W will also change. That product W is then used to compute the weighted sum. That's how it goes. So done is asserted 0 because you have not completed the sum of all the input layer, all the input pixels. Once you complete the weighted sum for the neuron, that means your address is equal to in size. When your address is, the moment it is 196, when my address becomes 196, this means my module knows that okay, all my inputs and weights are all the inputs and weights weighted sum is accumulated, and I have completed my addition. So I now need to assert my done to indicate that yes, the neuron module output is ready to be used. Okay, so then the moment you reach 196, I know that my computation is completed. So your done is asserted to be 1. And then at the end, after, upon this weighted sum, W0, X0, W1, X1 till W195, X95, you add the bias at the end. Because we have discussed that there is only one bias that is supposed to be added to a neuron out, but there are multiple weights and multiple inputs. So here at the end you add the bias and you pass the final output to your neuron out, and you assert the done and you pass your neuron done to your next parent module, which is your dense layer. So we'll discuss about that. Now we'll take a look at the introduction for your dense layer module. Okay, we'll take a look at the dimensions of the dense layer module. So input for the dense layer. What is the input for the dense layer? I know my input is xi. Size I know from the previous module 2w. And how many inputs are there? For the first layer 196. This is the first input layer, 196 pixel. Okay, that is connected. Let's take only one neuron here. Similarly, you have other neurons. Forget about that. So all these neurons are connected using some weights. So number of pixels and number of weights will remain same. But after that weighted sum is computed, you need only one bias. We have seen that in the previous neuron module. At the end, I'm adding the bias. But the weight and this input is being incrementally added in the out. Okay. So input I know that is 2w. And weights, how many weights are there? Weights, I know that there are, this is the width of the weight is w. There is 32 cross 196 weights. Okay, let's understand why I'm saying this. My first input layer contains 196 pixel. My fully connected layer contains 32 neurons. Okay, and my final output layer contains 10 neurons. This is my simple neural network for MNIST dataset classification. Now, when I say my fully connected layer has 32 neurons, for my first neuron, I will have 196 weights, because every neuron in your previous, every pixel in your previous layer, every input in your previous layer is connected to my neuron via a weight. This means my first neuron will have 196 weights attached to it from its input layer. Similarly, my second neuron of my fully connected layer will be connected via 196 weights from the input layer. Similarly for the third, similarly for the fourth, like this till 32 neurons, all my input layer is connected via a weight. This means how many total weights do I have for my first layer? 196 into 32. Okay, 196 into 32 weights I have, each of size 8 bits, or each of size w. For now you just remember w. For the sake of information, w I have kept it as 8 bits. Now bias, I know it is w, and how many bias do I have? For one neuron I have one bias, for this neuron I have one bias, for this neuron I have one bias. Okay, so total number of biases is 32. Now this weights array, I want to explain it once again. The weights will be a multi-dimensional array. We'll see how this multi-dimensional array is expressed in the code. So this is somewhat like this. See, total locations. Total location is 32. So this is my weight array, and I have 32 locations. Okay, so these are 32 locations I have. Why 32 locations? Because I know 32 neurons are there in the next layer. Now each of this location is divided into 196 parts. Why 196 part? For the 0th neuron, I know it is connected by 196 weights from the previous layer. Similarly, this neuron, the first neuron, is connected by 196 weights from the previous input layer. Okay, so for every neuron, there is 196 partitions. And in this partition, I have a weight value of 8 bits. Similarly, in this, I have a weight value of 8 bits. So what is this weight? For example, this weight is telling me the input pixel 1 is connected to your neuron 1 in the fully connected layer via this weight 0. This is not neuron 1, this is neuron 0. So basically, this is this first input pixel, or sorry, 0th input pixel connected to your 0th neuron via a weight W0. This is what this 8 bits is representing. Similarly, this is the second input, the first input pixel connected to your first 0th neuron. First input pixel, this is 0th input pixel, okay. 0th input pixel connected to 0th neuron via weight 0. And now here this is first input pixel connected to neuron 0 via weight 1. Like this, it goes on till 196. So this will see in code how this multi-dimensional array is being represented. Okay, so this is the dense layer code. We have seen that the input is 2W and 196 inputs we have seen. Weight, I know there are how many weights do I have? 196 into 32. So in size is 196 and neuron NB minus 1. Neuron NB is basically 32. So I have 32 neurons. Each has 196 weights connected to it. So I have 32 into 196 weights with me, and each of size width. Biases, size width. And how many biases do I have? For one neuron, I have one bias. So 32 biases I have. Neuron out is there, which is size 4W. And your neuron out, I know every neuron has one output. So I have 32 output from my first layer. I'm talking about first layer. Okay, so these parameters will change. For your second layer, these parameters will change. For now, just remember these parameters as 32, 196, 8 with respect to your first layer. Okay. Neuron done is a reg that is declared, and this is a reg done which is initialized to be 0. So this value will change once the computation of all the neurons in the first layer is completed. Once the weighted sum of all the neurons in the first layer is computed and that is completed, your neuron module will send a signal of done equal to 1, and that's how I know that okay, the first layer computation is done. Okay, so what this is doing, this line is basically declaring the array of instances. How do I know that? See, this dense neuron 0 is to neuron NB minus 1. This neuron module is called for these many instances. So this is basically array of instances. How many instances are being called? 32 instances for now. For why neuron NB is 32 now? Because my first layer, fully connected layer has 32 neurons. So these many 32 neurons, parallelly I'm calling the neuron module. So what it is doing, parallelly the neuron module for all the neuron will be called for my fully connected layer, and parallelly the weighted sum Wx plus B for first, Wx plus B for second neuron, Wx plus B for third neuron is parallelly computed. And parallelly, when you see, okay, the done is equal to 1 for first neuron, done is equal to 1 for second neuron, done is equal to 2 for third neuron. When the done is asserted for all the neurons, when this done is asserted for all the neuron modules, that is how I know that computation of my first fully connected layer is completed. The output for my first fully connected layer is ready when I know that neuron done is equal to 1, and neuron done here is a 32-bit output. 32-bit output, and each bit represents the done for every neuron. For example, 0th neuron done is asserted when the computation is completed for the 0th neuron. Wx plus b is computed for the 0th neuron. For the first neuron, when Wx plus b is completed, this neuron done for the first neuron will be asserted. And similarly, it will be asserted for all the 32 neurons. When 32-bit 1 I am getting, when this 32-bit 1, if this condition, At every clock edge, it is checked if neuron done is equal to 1. This means when this is basically 32-bit 1. Okay, when I get a 32-bit 1 here, that means all my bits, all the neurons of my fully connected layer has completed its computation. That is how I know that my dense layer output is ready to be passed on to my next layer. Okay, that is what is happening in dense layer. And dense layer basically declares a array of instances, and this can also be done in a different way. This can be done using generate, but since all my neuron modules have same set of input ports, same set of parameters, that's why I have done it using array of instances. Generate also you can do, but this is also the other way of doing it. So yeah, when done is asserted, that means all my neurons have completed, all the arrays has a done equal to 1. This means the dense layer output is ready, and you complete assign the layer done to be 0, sorry, done to be 1. Layer done 1 means okay, the layer computation is done, you can move on to the next fully connected layer or next output layer.